Good evening, everybody. My name is Dr. Jessica Barnes. I'm an assistant professor at the Lunar and Planetary Lab at the University of Arizona. Thank you for joining me on International Observe the Moon Night. I'm really happy tonight to talk about the scientific value of lunar samples. Now, planetary science is focused on trying to understand the composition and content of our solar system, trying to assess what processes are happening on the surfaces and interiors of planetary bodies, and ultimately trying to understand how the planetary system we have today was formed and evolved. What are its origins? We can learn an awful lot about a planetary body by remote observation, either from Earth through telescopes or from orbit around a celestial body. We can also learn a lot about a planetary surface by going and visiting it robotically. But for a planetary geologist, samples and being able to study those samples is really crucial to ground truthing what we learn from those other methods. Samples returned to Earth really offer us an opportunity to use advanced analytical techniques only available on Earth to unravel the origin and evolution of those planetary bodies. And those studies just are not possible at the moment on other bodies because we can't ship those types of instruments and laboratory equipment on spacecraft. Now, lunar science is truly grounded by the information we've gained from lunar samples, whether Apollo or lunar samples or even lunar meteorites. The chemistry of Apollo samples helps us to constrain density models, for example, for lunar crustal thickness constraints. We find exogenous material in Apollo and lunar samples that informs us about the types of materials that were impacting the Earth-Moon system through time. Apollo samples also provide information on the geological and geochemical makeup of the moon, and that in turn informs our models of how the moon formed and evolved, and maybe how other similar sized bodies may have formed too. From studying brecciated material, like the sample shown in the middle of the screen, we learn a lot about impact processes and how those affect and change the surfaces of the moon. When we think about studying lunar samples on Earth, we're really talking about two main things. We're talking about either studying meteorites or we're studying samples that have been brought back through sample return. Meteorites are really a free sample that fall to Earth after impact. They fall to Earth after an impact with the moon sends material into Earth crossing orbit. We collect meteorites on the surface of the Earth, either as witnessed or observed falls, or we go out and find them in hot and cold deserts. Meteorites are really an excellent complement to the lunar and Apollo and Luna samples because they represent an effective random sampling of the lunar surface. And as we'll see in a second, they sample areas outside of the regions that we've already visited. The other non-free way to get lunar samples is to go to the surface and bring back samples, either robotically or crewed. And that's really going to be our focus tonight. A total of 9 lunar missions returned samples from the lunar surface between 1969 and 1976. As we all know, there were 6 crewed Apollo missions, 11, 12, 14, 15, 16, and 17. And they collectively brought back a lot of material, 382 kilograms of lunar material. Whereas the 3 robotic lunar missions that operated over a similar time brought back only about 300 grams of material. And the difference in the return mass is really a direct result of having humans versus robots on the surface, and also having the ability, in the case of the later Apollo missions 15 through 17, having the ability to traverse larger areas with a rover. So crucially, all of these sample return missions return materials from the near side of the moon, as you see depicted in this graphic. There have so far been no missions to the poles or to the far side of the moon. And so in some ways, although we've visited several different sites on the surface of the moon, we're fairly geographically and geologically restricted in what we've been able to access and bring back to Earth, and also in turn, what we've been able to learn from the moon. We've learned a lot, but as you'll see later on, there are lots of things we still don't understand fully. And so tonight I'm going to focus on 2 Apollo missions and tell you a little bit about some of the major findings that we've had from samples from those 2 missions. And we'll start off with Apollo 11. So Apollo 11, as you all know, landed in the Mare Tranquillitatis region, or Sea of Tranquility, on the lunar near side in 1969. And here's a beautiful Lunar Reconnaissance Orbiter camera image of the Apollo 11 landing site. You see it on the right. You can see the position of the lunar module, which is indicated by LM, or LEM as it's traditionally called. And here's a photograph from the Apollo era and from that mission of the LEM on the surface. You can also see in these really high resolution images the astronaut tracks, where they traveled on the surface. You can see their movements as they're deploying experimental packages and taking photographs and collecting samples. Overlaying on the right side, sorry, the left side of the screen, are the tracks that those two astronauts, Buzz Aldrin in blue and Neil Armstrong in orange, the tracks that they made while they were doing those operations on the surface. Now, this was the very first lunar mission to the surface and with humans, and they didn't have a lot of time to explore. They only had about 2.5 hours. And so with no roving vehicle, they didn't really get very far from the LEM. This is illustrated in more easy to imagine terms if you look at this diagram or this figure. And so this is the same Apollo 11 tracks to scale, overlaying on the Intrepid Sea Air and Space Museum in New York City. And you can just see that they didn't get very far. Despite that, the samples that Aldrin and Armstrong collected and brought back proved vital for not only setting the stage for huge discoveries about how the moon formed and evolved, but those samples are still being studied today and revealing new insights as we study them with new techniques. They're giving us new insights into the moon's history. I'm going to talk about one particular example of how Apollo 11 samples have helped constrain new insights into how we think the moon formed. And the example I'm going to give is Apollo 11 soils. Now, when we look up at the moon, even from Earth, we see two different terrains. We see a darker terrain and a lighter terrain. And very simply, these represent two different geological units. The darker regions are the mare, the volcanic regions, and the highlands represent the crust. Now, even before Apollo 11, some researchers had already postulated that the mare would be lava lakes or lava seas, and that the highlands could be the original crust of the planetary body. Upon the return of Apollo 11 samples and studying those in the lab, like the one you see here, it was revealed that actually these soil samples contain a wide variety of different rock types or lithic clasts. And you can see the example that we've got here, they range in size. These are quite small or fine-grained materials, only a couple to few millimeters in diameter. But crucially, they're made up of different materials. I've indicated two different types here. We've got basaltic material as indicated in the lower right, and anorthosite. And it was really the discovery of this anorthosite, which is a rock type made up predominantly of one mineral, calcium-rich feldspar, that really sparked models for the formation of the moon, new models for the formation of the moon and evolution. And that's because anorthosite, made up of this calcium-rich feldspar, while that mineral is not rare on Earth, actually it's one of the main rock-forming minerals, finding it in large abundances and finding anorthosite in large abundances is rare. There needs to be almost a global mechanism for trying to create that much anorthosite if we think that this lighter colored rock type actually makes up the lunar highlands. And so that sparked two teams suggested new models in the 1970s, only less than a year after having the samples, new models for how the moon thermally and chemically evolved. And those teams were led by John Wood and John Smith. And so in both models, the moon starts off after accretion very hot. And you can see that in this lovely Goddard Space Flight Center graphic of what the moon might have looked like while it was still largely molten, but starting to form rocks on the surface. And so both of the initial models from the 1970s start off with a moon that is mostly magma. It's a magma ocean, or we call it the lunar magma ocean model for the evolution of the moon. And the depth to which this magma ocean existed, whether it was whole moon, as you see depicted in the cartoon, or molten to some depth, that's still debated. But we'll just proceed with this cartoon image that's shown here. So the moon starts off mostly molten, but then it starts to cool down. And as it cools, minerals start to crystallize out. And we think that magnesium-rich minerals like olivine and pyroxene would have been the first to form. They would have been more dense than the liquid from which they were crystallizing, and so they would have fallen or sunk to the bottom of the magma ocean and crystallized upwards and built upwards through the mantle over time. At some point, though, about 80% solidification of the magma ocean, the liquid has changed composition and also has changed temperature. And so at that point, you start to crystallize like new minerals. And that's when anorthite comes into play. Anorthite will crystallize, but it will be less dense than the melt from which it's crystallizing from. And so being less dense, it will want to float. And so anorthite, we think, would have floated in this magma ocean liquid that was left and actually formed the crust or skin of the moon. And so that's the general model for how we believe the moon would have formed a largely anorthitic crust or an orthositic crust. And so getting Apollo 11 samples to Earth and into the laboratory where they could be analyzed and studied by geologists really changed the way we view the moon as fundamentally and as early as 1970. And this model, the lunar magma ocean model, is still widely used today. There are different variants on it, and we understand it a lot more through experimental geology and doing experimental petrology in the lab. But as I said before, these are very early models, are still the basis on which we still understand how the moon thermally and chemically evolved. Now, the next science case study that I want to look at is Apollo 17. And there are a few interesting things. There are many things, but few I want to focus on about Apollo 17. Now, Apollo 17, of course, landed in 1972 in the Taurus Littoral Valley on the eastern rim of Mare Serenitatis that you can see here. And here, like we had before, you can just see the difference between what happened in Apollo 11 as indicated by the yellow circle around the Intrepid. Remember, the footprint of the Apollo 11 astronauts is actually much smaller than what's indicated by that oval. And in comparison, you see in the orange tracks, the traverses that the Apollo 17 astronauts, Eugene Cernan and Jack Schmitt, took. You can see they did 3 EVAs, and they were really able to travel that long because of 2 reasons. One, they had a lot longer on the lunar surface. So in comparison to Apollo 11, that only had 2.5 hours to explore, the Apollo 17 astronauts had about 75 hours to explore. They were able to travel much further because they had a lunar roving vehicle, an LRV. And so they were actually not only able to travel longer distances, but actually bring more material back because they had a way of bringing them back. During that time, they collected around 111 kilograms of material. And so you'll remember back to the beginning that the total Apollo program brought back 382 kilograms. And so Apollo 17 was really a really heavy player in bringing back a lot of material. Okay, so similar to what we saw for Apollo 11, here you see a Lunar Reconnaissance Orbiter camera image with the traverses the astronauts took and crater names and pit stops located on the, shown overlain on the image. Now, the point I want to make here as well is that one major advantage to sample return with crew is that we get geologic context to the samples collected. And actually, Apollo 17 was the only mission to have a fully fledged geologist on board. And so having someone who can critically evaluate the samples that can be collected, noticing new opportunities for sampling, noticing, humans notice things that are a little out of the ordinary. Having those instincts and those opportunities really made a big difference on Apollo 17 and with the Apollo program in general, highlighted the value of having humans on the surface of another planet. Okay, so what I want to focus on here is one particular station on Apollo 17, and that's Apollo Station 6. And so here you see a high resolution narrow angle camera image of a boulder complex at that Station 6 location. And you can see that we have, even with these high resolution images, we can see a boulder trail. So this boulder that you see in the middle rolled down this slope until where it's located today. And the Apollo 17 astronauts sampled that boulder complex. And you can see that illustrated by the cartoon on the same slide. All of the numbers beginning with a 7 indicate Apollo 17 samples. That's the nomenclature used for Apollo 17 materials. And this just beautifully highlights that we know exactly where these samples were taken, and that highlights the significance of actually being able to go somewhere and collect a sample with known geologic context. Some of the rocks shown in this cartoon have not only helped us understand the chemistry of the lunar highlands, the lunar crust, and lunar magmatism in general, but some of those rocks have been dated to more than 4.2 billion years old. And so they also allow us to constrain the age of the lunar crust, and by extension, the duration of the lunar magma ocean. And so they really have been very critical in helping us address and understand how the moon formed and evolved. Another interesting find of the Apollo 17 mission was the discovery of sample 74220, which is an unusual soil sample that was discovered at Shorty crater, indicated by the picture on the left-hand side of your screen. The sample is part of a volcanic eruption on the moon that formed a pyroclastic deposit that you can see here. And we think that this deposit and these samples are about 3.5 billion years old, so also very old compared to things that we have easy access to on Earth. Most of the sample consists of orange glass spherules. You can see those indicated here. And these are basically small lava droplets that didn't have time to form minerals before they cooled. And so on the right-hand side of the screen is how we think these formed. So we have a volcanic eruption from a vent. We have these lava droplets spewed out. And because the moon didn't have an atmosphere, they essentially quenched in that vacuum and then fell back to Earth as these glass spherules that have now been sampled. An important legacy of the Apollo era studies of lunar samples was that the moon really lacked, and all the lunar samples lacked hydrated minerals. It was very hard to find lunar water in any of the samples that were brought back using the technologies available at the time. And also orbital missions up until the mid to late 2000s hadn't been able to detect definitively any water on the surface of the moon. That was until the mid to late 2000s when a series of missions, including the one that I'm showing an image of here, Moon Mineralogy Mapper, a NASA instrument that flew on the Indian Space Agency's Chandrayaan-1 mission, found hydroxyl and water all over the lunar surface, but particularly at the lunar poles, as you can see in this figure. And so concurrently, and thanks to advancements in laboratory mass spectrometers, at around the same time, water was also found in lunar samples for the first time. Definitively, we could say this was lunar water and not terrestrial contamination. In 2011, water was also found, detected in tiny micrometer-sized melt inclusions trapped in olivine crystals within those same orange glass beads. And these results suggest that parts of the lunar interior might be as wet as some portions of Earth's mantle. So a complete 180-degree turn on what we thought during the Apollo era, that the moon was bone dry. Now we know actually there is lunar water both in the interior and on the surface. And together, these types of studies have really sparked a revolution in lunar volatiles research, both looking at lunar magmatic volatiles, those in the interior, and those on the surface. And how can we use those volatiles and those water-rich ices on the surface as resources for future exploration. Last year, a new initiative was released to study unopened lunar Apollo samples. Those are samples that have been returned to Earth with the other Apollo samples. They were either photographed really quickly or there was minimal analysis done on them, but then they were specially curated, specially stored under different conditions for future generations. And so many of those samples have not been studied or looked at or even opened for 50 years, and some haven't even been opened since they were collected on the lunar surface. Since we're now in the future, we're in 2020, NASA decided to release some of these previously unopened samples through the Apollo Next Generation Sample Analysis Program. And so one of the samples is shown here on the top slide, and this is an X-ray scan of Apollo 17 sample 73002. It was collected on the Apollo 17 mission and is part of a double drive tube or a core sample. So this is one of two samples. Before it was locked away, it was X-ray scanned, and that's what you see on the top panel. The image is a bit blurry, but even from that image taken in the 1970s, you can see some detail. You can see there's sample in there. That's a good start. You can also see that the colors are different. So brighter material will be more dense material, more dense minerals, and then less dense material will appear darker. So we can tell that there's some heterogeneity, some different lithologies in there. But then it was locked away for 47 years until last year, when it was scanned again using new technologies. And you can just see the difference here. It's higher resolution, the image. We start to pull out things that are very small, micrometer size objects. We start to see bigger differences within class that previously had looked like they might all be one material. Now we see there are differences. And so after it was scanned using a new generation micro X-ray computed tomography scanner, the sample was opened. And here you see the wonderful curators at NASA's Johnson Space Center having just taken the sample out of its container and put it onto the processing bench. And you can see the beautiful sample laid out here. And so this photograph is taken before they started dissecting and subsampling the core to then give it to the science team. Now, this initiative is being run like a modern day sample return mission, a big Apollo style sample return mission. The team consists of over 50 researchers from across the world, and it links together several generations of lunar scientists, so very early career and then Apollo era scientists as well. It presents an opportunity for us to learn new things about the history of the moon, from a sample that has never been studied before, from a geologically very interesting region of the lunar surface. And it also allows us a really good opportunity to understand what worked and what didn't work with Apollo sample curation in order for us to better prepare for samples that might come back from Artemis and other sample return missions. Now you're probably asking yourself, well, why are we talking about going back to the surface of the moon to collect more samples? Is future sample return really needed? And the easy answer is yes. We have a lot of information. We've learned a lot from the Apollo lunar samples and also lunar meteorites, but we don't have true diversity. Most of our samples come from this geologically restricted area on the lunar near side. And we know from orbit that, and from probes that have gone to the surface on the far side, that there's a lot to be learned from moving outside of this near side region of the moon. So far in the collection, we don't have any pieces of the lunar mantle, which would be crucial to helping us pin down its thermochemical evolution. We don't have any samples definitively from the lunar far side that we probably have in meteorite samples, but we don't have the geologic context that goes with those. And so going to the far side is really important. One of the largest, if not the largest, impact basin in the inner solar system, certainly in the moon, is South Pole Aitken Basin, outlined here in the black dashed line, and you can it's at the lunar South Pole, and it had the potential to expose mantle rocks at the surface. Also, dating such an ancient and old basin would be really important for constraining lunar crater counting and also extending that to other planetary surfaces. Importantly, we now know that there are lunar polar volatiles, and so we need to be able to go and sample those and understand, are they really a resource that we can use for future exploration, not only of the moon, but of the solar system. And also to just understand how they formed and evolved, and how what their character is, what their composition is. So we still have a lot to learn about the lunar surface, and I've just gone through a couple of examples, but we really need more samples to better constrain how the moon formed, And that will in turn help us to inform us about how the Earth formed as well and what was impacting the Earth-Moon system over time. We see the action of plate tectonics on Earth, and it's really erased the very earliest record we have of what was happening on Earth in the Hadean and very early on. But that record is preserved on the Moon, and so the Moon really is a touchstone for understanding early solar system processes. So we still have a lot to learn from lunar samples and lunar sample return. The future really is lunar exploration. I just mentioned lunar polar volatiles, and these are really, the poles are very geologically interesting. And we now have several programs that are targeting the lunar South Pole to go and look for water ice. You can see ice exposures indicated on this South Pole projection of the lunar surface. Several missions have been proposed to go very soon to the lunar South Pole to characterize those volatile elements, to see what their lateral distribution is like, how they change with depth, what their chemistry is. Do we only find them in permanent shadowed regions of craters, or are they all on the lunar, all across the lunar surface? And so, two missions that I'll just focus on really quickly are the European Space Agency's Prospect package, which is a package for resource observation and in situ prospecting for exploration, commercial exploitation, and transportation prospect. And it will operate on the lunar surface of the Moon as part of a Russian mission, Luna 27, and that's slated to go to the Moon in 2022 and visit the lunar South Pole. In parallel, NASA has announced, as early as this week, they announced their new lunar exploration plan that includes VIPER, which stands for Volatiles Investigating Polar Exploration Rover, VIPER. And it's a mobile robot that will go to the South Pole of the Moon and again, characterize the volatiles that are there and give us an idea of, it's kind of like a scout or a prospecting mission, go out and see what's there for us to determine whether it's useful to go and further explore those volatiles and then potentially use those as a resource. And so VIPER is planned for delivery to the lunar surface in, I believe, 2023. And then, of course, the Artemis program at the moment concludes with Artemis 3, which will see humans on the surface of the Moon again at the lunar South Pole potentially in 2024. And part of that mission will be to collect samples, as you see in this beautiful NASA illustration here, collecting samples from the surface of the Moon, as I say, in 2024. And so there's a lot of exciting lunar exploration that's planned, and we really need samples to be either analyzed on the surface by robots to give us an indication of what's there, but really we want lunar samples to be brought back from a different area of the Moon so that we can test and refine our models and build new hypotheses about how the Moon formed and evolved. So thank you very much for joining me tonight. And with that, I will take any questions. Thank you.